Hi, in this video we'll discuss about equilibrium porous media adsorption of water vapor onto the silica gel. So generally if you see in any porous media, so if these are the pores and if this is the gas that is entering in, right? So when it comes in contact with these silica particles, so if the water vapor, for example, the fraction is 1, after it comes in contact with the silica gel, the fraction now becomes 0.7. It means 0.3 fraction is adsorbed onto the silica gel particles. Now, if you try to zoom in this single particle, so it will be this kind. So now the water vapor will be adsorbed on here, right? Okay. After adsorption, this silica gel has the capability to travel until the center point, right? Obviously surrounding if it also has been absorbed by the vapor, so think in this way. So it is completely has an adsorption on the surface of the silica gel, so all this vapor can travel up to center point, right? So this traveling of the water vapor until the center point is depend on, will be depend on diffusion coefficient. So the diffusion coefficient of water vapor in silica gel, right? So there is no convection term here. There is no flow of water vapor inside the silica gel. It is only diffusion that will be present inside the silica gel particle. So water vapor traveling into the silica gel particle mainly depends on the diffusion coefficient. Okay, so if the diffusion coefficient is high, the adsorption which takes place on the surface, immediately the water vapor will be going into the center. If the diffusion coefficient is low, the water vapor will be stagnated at the surface, and here there will be low concentration of water vapor. So more water vapor will be present on the surface, no water vapor at the center. So this kind of particles are not recommendable, because anything that gets adsorbs the water vapor, if travels into the center, so more of water vapor can be adsorbed onto the surface. So the diffusion coefficient should be high. So any gas that has a diffusion coefficient more with respect to the adsorbent, that is preferable in adsorbent case, right? So now one is the mass fraction of the water vapor that is coming in contact with this is silica gel, and zero point 0.7 is left, remaining 0.3 will be going into the silica gel. So whenever anything gets adsorbed onto the silica gel, I'll just remove this. Remove completely. So anything which gets adsorbed onto the silica gel, so there will be heat generation, that is called heat of adsorption. Heat of adsorption, right? So when silica gel comes in contact with water vapor, due to the adsorption of water vapor, there will be a heat generation, right? So that heat generation depends on the amount of adsorption onto the silica gel, and that here it is been given as dou x by dou t, right? So dou x by, sorry, it's dou x by dou t, where x is the units of x is kg of water vapor onto kg of silica gel. So this is x units. So it is a kg of water vapor that gets adsorbed onto the kg of silica gel. So if this change in dou x by dou t is high, then there will be more heat of adsorption that will be generated in the silica gel. Okay. So now this dou x by dou t is the important term which we need to calculate. So initially each and every particle has zero water vapor, right? So all these have zeros. But as the water vapor gets adsorbed, the temperature of this will rises due to the heat of adsorption, as well as for the new water vapor to be adsorbed onto the surface will also depends on the existing content of water vapor that is present in silica gel. So that is the reason why we need to calculate this dou x by dou t. What is the rate of change of silica water vapor that is being adsorbed onto the silica gel? Okay, so now if you take in this way, x is the amount of water vapor present in the silica gel, so that will be equal to x naught. I mean the amount of water vapor present in the previous time step. So I'll be writing in this way. This will be more amicable for understanding. So x at current time step is equals to x naught, or else it is the x at previous time step, which I'll mention it as x naught, right? Plus rate, which is dou x by dou t into time step, right? So this is the amount of water vapor that is present at any time step. This depends on the previous time step and the rate at which the water vapor is being adsorbed onto the silica gel into the time step of the simulation. Okay, so now here the important term here is, if you start from the zero, so the content of water vapor initially at the previous time step means the initial time step it is zero. Now it depends on dou x by dou t. So dou x by dou t is related by this equation. So this is Debian equation. Debian equation in which it depends on activation energy. This Ts is called as the temperature of the medium. But for example, if you have a domain like this and it is discretized into, maybe if you take this as the discretization elements, so it depends on the temperature of the cell, which is Ts, and the x infinity is again given by this empirical correlation. In this x infinity, it depends on Ts, which is cell temperature, and Tsat. Tsat is nothing but the saturation temperature of this cell. So saturation temperature means it depends on saturation pressure, right? So for the existing Ps, if you assume that Ps means the existing pressure in that cell, if that is equals to Psat, then what will be the Tsat, right? So this is the thing what we need to look into. So the Tsat is nothing but depends on Psat. Psat is nothing but Ps, and there is a correlation for water vapor for the saturation temperature and pressure that we can give using Antoine equation. So that Antoine equation helps us in order to find this Tsat. So finally we'll be getting x infinity, as you know Ts, and as you get x infinity, you know x, which is the amount of this water vapor present per kg in that cell. For initial it is 0, I mean for the initial time step, so this will be 0, and that you can calculate dou x by dou t, which is d square is nothing but the particle size here. You will have the particle diameter, right? So that is dp, I mean d square or dp square, anything it can be, right? So now dou x by dou t is dependent on this entire correlation. Once you get dou x by dou t, you will substitute here. Once you substitute here, you know the time step size. Initially it is 0, or else it can be have some other value. Then you will be getting x current time step fraction. So now in the second one, now x current time step will be equals to x previous time step, which is this one. Okay. So the x previous time step is now the previous current time step, plus again dou x by dou t you need to calculate for every time step into time step what you considered in the simulation. So again this dou x by dou t calculation will be using the same formula. Okay, now I will remove this stuff. So now once you get the stuff dou x by dou t, so now this is the amount of mass of water vapor that will be removed from the surrounding fluid, that is water vapor. So if that is removed, that will be adhered or adsorbed onto the silica gel. So the amount that will be removed will depends on the porosity as well as the volume of this, or the density of the silica gel into the rate of adsorption, right? But we are giving here 1 minus porosity because that depends, or that the amount that will be adsorbed depends on the fraction of solid present, not the fraction of vapor present. So the fraction of solid present is nothing but 1 minus fraction of vapor present into density of solid into dou x by dou t. So the unit should be in the kg per meter cube when you try to substitute in any UDF in Ansys Fluent. That's the reason why I'm taking this. So now if you consider, this will be kg per meter cube, and dou x by dou t has no value because that is already kg per kg, right? And here, sorry, this is kg per meter cube second, and this dou t has already have a unit second. So finally we'll be getting kg per meter cube second. You can substitute this in the continuity equation of the gas. So as it goes on to that side, this will be a negative term, right? This is the source term. It means the amount of water vapor that you need to remove for every time step as it is being removed from the surrounding fluid and getting into the silica gel solid. Okay. Similarly, so it also generates heat. The heat also depends on this, the solid presence, that is 1 minus epsilon t into density of that solid, and to dou x by dou t, the rate at which the water vapor is being adsorbed onto the solid, and is this QAD, the heat of adsorption. So when you try to multiply this value, this is the extra amount of heat that will be added onto the domain or the cells for every time step. So these are the two variations or two changes you need to make to continuity equation and energy equation of the gas in the porous media to account for the adsorption of water vapor or H2O gas onto silica gel, right? But in this both addition of the source terms, it depends on dou x by dou t, and dou x by dou t is calculated by using this correlation. In that, x infinite is again calculated by the below correlation, right? So these already been derived in, a UDF has been derived with respect to those equations. I'll just showcase it to you. So now this is the UDF what I'm talking about. For every time step that is define executed end, I'm trying to calculate the rate, which depends on the equivalent or x infinity what I'm talking about. And this rate has a term A equivalent, and equivalent has the saturation temperature with respect to the pressure. That is been calculated again using this Antoine equation. So this what you're seeing is an Antoine equation. So from that I have calculated the temperature, and I've substituted or that the rate dou x by dou t, I have used that and stored in a user defined memory called c underscore udmi c comma t1 comma 2, and that I have again used in the source term. As you know, the source term is dependent on dou x by dou t, rho s, and 1 minus epsilon t. Here my 1 minus epsilon t is 0.67. It means epsilon t is 0.33. Sorry, it is 0.37, and this is 0.63. Okay, that is what I have substituted here. And in the density of silica gel, that is 2027, and c underscore udmi c comma t comma 2. Similarly, for energy source, same thing, everything repeats with the heat of adsorption, that is 2.693 into e power 6, right? So this is the equation. Maybe I'll just show you this geometry what is present on the screen here. So this is the geometry. From here, the water vapor enters. As it enters, this is the silica gel that is present. So it flows through the silica gel. It's the porous media, and the sum of the water vapor gets adsorbed, and the temperature of the silica gel rises due to the heat of adsorption, and the remaining water vapor goes out of the outlet. So here the temperature is, if it is 300 or 298 or 280 Kelvin, for example. So when it comes out, the temperature may raise up to 320 Kelvin or 315 Kelvin, anything depends on the rate at which it is being adsorbed. Okay. So I'll just showcase you the geometry. I think you have seen it, but I'll just show it to you. So this is the geometry. This is silica gel and this is the fluid. And you can see this is one inlet and this is outlet. Okay, this you can check here. The inlet is this one. I have named it as inlet, and outlet is this one. I have named it as an outlet, and this is the silica gel wall. The remaining internal is an interior because these both are the fluids, so we need to consider this as an interior. Okay, so then you'll be going to meshing. It's not that complicated, very simple case what I have taken. So but it depends on your complexity, you can work on. And here I have considered only a student version, so my mesh count is limited to 1 million, and I've taken it accordingly. So I've used a fluid meshing. If you want, you can use Ansys meshing also. It depends on your flexibility. So once it's been opened, then you need to go to the watertight geometry in the workflow situation. So what here I'm talking about is an equilibrium case. So where there is no interaction between solid media and fluid media separately. But in the next tutorial, we'll discuss about the interaction between solid media and fluid media separately, and we'll show you how the UDF changes and what is the physics behind that. So you need to go to workflow instead of outline geometry. After going to workflow, you need to select watertight geometry, and going to import geometry, try to import and then add local sizing. So I have given no and update it. The generate surface mesh, I have taken this mesh count with the curvature as 30 because this mesh count will help me in having a count less than 1 million. And then update or generate surface mesh. Then go to describe geometry, say that you have only fluid regions, and you just stick a wall to internal because the region between those two fluids should be internal, not should not be a wall, and create check on apply shade topology. After that, you describe, click on describe geometry, apply shade topology, click on apply shade topology, update the geometries. These are the geometries boundary conditions what we need to have, and accordingly we need to update region, both are fluid, and add boundary regions. I have added just the three normal boundary layers, and then go to surface mesh, and you can just click on polyhedra and click the surface mesh, and just go to the generate volume mesh. After the volume mesh is generated, go to switch to solution, then you'll be going to the solution. Okay, so I'll just open for you. You need to, you can use only 4 cores. Double click on setup, just 4 or 3. So once this opens, so we're using 5 to 6 user defined memories. So you need to go to user defined and you need to check on those memories and increase the memory count to 6 or 7, depends. And then as I've shown in this UDF, in order to update the mass fraction of water vapor kg per water vapor per kg of silica gel, that is x, that I'm trying to store in the user defined scalar, which is equals to user defined scalar. It means previous time step value and plus rate into physical underscore dt. Physical underscore dt is nothing but I am trying to get the physical time step size. So time step size, what you are taking in the setup case. So here the time step is 0.0001 minus 4. Okay, so click on transient. So y equals to minus 9.81. So in the down direction. So in the materials, turn on the energy and viscosity as SST K omega. In the fluids, select the water vapor, and this is not alumina, so this is a silica gel. So click silica gel. The density is 2027. Thermal conductivity is 0.3, and this is 970. It is SL, change create, yes. So in the materials tab, go to materials tab, create edit. In the fluid database, go to fluid, go to water vapor, copy, close. Automatically water vapor will come in this. So this is my silica gel fluid and this is a normal fluid. So go to silica gel fluid. So you need to activate the porous zone, activate the porous zone, and here the porosity is 0.37, and this is the equilibrium condition of the silica gel. Okay, click on apply, close, then go to user define. In the memory, increase the memory count to 5. In the scalars, give it to 1. In the selected zones only, try to select silica gel, remaining none. Then go to function hooks, compile, add. You can see that UDF present, the equilibrium case, add it. So everything added without any issues. Load that. So in the function hooks, add executed end. Okay. In the source terms, you try to add mass source and energy source for both for the silica gel fluid. Right, in the next video we'll discuss about non-equilibrium. There will be two things then, fluid as well as silica gel solid. Okay, in the boundary conditions I have given as a pressure inlet 1280 Pascal with a 285 Kelvin as an inlet, and outlet I have selected a pressure outlet. The pressure outlet 01 and back for temperature is 300. And in the methods, so these are all the normal methods for the default methods have left. In the equations, you should not solve user defined scalar 0 because we are not trying to solve it. We are trying to have a replica of it where we are trying to mimicking the solution by just impregnating these things. That's it, right? And we are trying to calculate. Okay. Then go to initialization, initialize, and then you can just have an setup here your counters. The counter 1 shall be selecting the plane 5, so user defined scalar compute 0, this will be 0 initially, so this is the thing. Then I'll be selecting the iso surface with the velocity magnitude as 8.94 and click save, close. Then I'll be going to animations, sorry, scenes. In the scene 1 I'll be selecting this counter 2, counter 1 as this, and I'll also create a new object called mesh, and the mesh I'll be selecting this. Now I'll click save display. So this is where how it will be looking upon, right? Okay, so this is one thing. And in the similarly scene 2, I have selected the counter 3 instead of counter 1, which is the temperature. So I'll click save display. So then will be the counter 3, I'll just show it, is nothing but the fluid silica gel with temperature as a counter. Okay. So now then I'll try to go to run calculation with this time step size and number of time steps. I'll click on calculate. So now after running for a few hours, so this is the kind what you can see here, the user defined scalar. I have given this auto range and the static temperature as this. So this is the ISO surface with a velocity of 8.9 what I have mentioned. So it is going out, and this temperature, the blue color means it is 285 Kelvin, and this is at a blue color means it is a 0 user defined scalar value. That is nothing but the kg of water vapor present per kg of silica gel. That is the x value. Now you can see the variation of this x, this kg of water vapor present per kg of silica gel, how it tries to change when this static temperature of water vapor getting struck onto this silica gel. So now you can see here it is slightly going to red, it is increasingly going to red. So now the temperatures you can see it's changing, it's 464 Kelvin, it's becoming more red. So it's now entirely turning into red. Now it is reaching the scalar fraction value. So this is for what is the amount of water vapor that is being absorbed. Accordingly, I have also created a second video, right? So this is the temperature variation in the silica gel. You can see the temperature is increasing, getting varied due to the convection and everything. And see, it's finally reaching to the very high temperature, so 470, 465 Kelvin. Right. So hope I think you understood and enjoyed the lecture on this silica gel adsorption. If you have any doubts, you can drop a mail to the mail ID attached to the video. Okay. Thank you.